I will. I will begin. Dear Father, we thank you for this day again. I thank you for this class. Just ask you to be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right. So it's my first time experimenting with an arm wrestling component to Math Battle. I'm pretty happy with how it went. As far as I can tell, no one got hurt, so that's good. So if you didn't notice that I posted a problem 22 to Math Battle 4, it did happen. I mentioned this in class. Of course, it's easy enough to not have heard that, and I understand if you didn't. That said, it doesn't really matter if you didn't do it, because that's not the required portion of the course. You can still make an A without knowing anything about that. So you guys have any questions about anything in particular? I'll run through the solution to the Math Battle. Try to do it pretty quick here. So here, the basic idea is just to notice that these are oriented, let's see, if we think about Pac-Man with whatever that would be, I guess that's an eye. What would that be? I don't know. A mole? Maybe it's been shot or something. I don't know. But let's see here. So it's the outer edge is oriented in the positive counterclockwise sense, and the inner edges should be oriented in the counterclockwise, clockwise sense. But well, this one, wait a minute. No, these are both oriented opposite the way they're supposed to be the positively oriented boundary of a region with holes, right? So that's why I have that the boundary of R is C union minus C1 union minus C2. So because, on the other hand, the integral around the edge by Green's theorem with holes is this, but this is given to be 0, right? Because the difference is the same, so that's 0, and consequently the integral over C is the integral over C1 plus the integral over C2, which happens to be 13 here. So there's about a dozen different variations of this problem. The point of it is to test on your understanding of the orientation of curves and how Green's theorem requires, a very particular choice of orienting the outer and the inner edges of a region. It is not conservative. Remember, we spent considerable effort to prove the equivalence of 4 different characterizations of a conservative vector field, right? It's the gradient of a potential, path independence, integral around loops is 0, or in the simply connected context, the closed condition, right? Which in 2 dimensions becomes what I have up there, partial p partial y is partial q partial x, or in 3 dimensions, the vanishing of the curl, right? So we have these 4 different ways of characterizing a conservative vector field in here. So no, it's not conservative. Integral around a loop is non-zero. Problem 3, do you want a problem like problem 3 on the test tomorrow? I mean, yes, obviously you do, right? This is a nice, easy problem if you have figured things out in terms of the conservative vector field. This one's a little bit tricky because, there's a mixture between the x and the y and the z. So every one of those terms does double duty in 2 different components when you differentiate, right? So that's kind of neat. Problem 4. This is pretty straightforward. I don't really have much to say about this. Is it possible to find a vector, a function f such that the gradient of f is equal to big F? In other words, is f conservative, right? And the answer is no, because we just showed that the curl is non-zero, and the curl would have to be 0, because we know that the curl of the gradient is 0. That's one of our fundamental vector identities. And let's see here. This one. I'm sorry. I mean, I suffered along with you guys, but I'm sorry about this. Like I could test on this without this happening, right? Don't ignore this problem because of the ugliness. Think about, what if this hadn't been the sum of 2 things? How much nicer this problem would have gone, But it's simple enough. We just have to parameterize the curve, which I think was given to us in this problem, and then work out the definition of the line integral, which, after some suffering, you get 41 104 divided by 35. I Googled it and got the same answer. So, and it used to be that Googling didn't make sense, but it's gone back to making sense again. I no longer Wolfram Alpha. I pretty much always Google. Blaze was very grimacing just now. It's very, very cartoonish. I appreciate that. But so this one here, basically, the idea is, I mean, there's different ways to do this, right? You don't have to use Green's theorem. You could just calculate the integral over each leg and add them together. That would also be a way to do this. But I think Green's theorem is more interesting because we can trade this line integral for this area integral, and it works out to 2. But of course, that is the integral around the whole square, which includes both the c that we're interested in, but it's in the opposite order, so I have a minus, right? And also c1, which I've defined to be the, path from 0, 0 to 1, 0. Any questions? Okay, so this one here, again, is a Green's theorem question. This one, though, probably, you want to use polar coordinates for, obviously, when you actually get to the area integral, because this is, a nice polar region. It's not such a nice Cartesian region, And also, x squared plus y squared should scream at you, use polar coordinates, right? And so I do, and it works out. And again, this one, the orientation issue is also at play here because this thing is oriented the wrong way. It's clockwise oriented, which means that Green's theorem doesn't apply, right? So I have to reverse the like this curve is the reversal of the boundary of R in the positive sense, right? So Green's theorem does require attention to the orientation issue, all right? Anyway. It's been a minute since we talked about this. I didn't talk about it too long, but we did talk about the flux of a vector field in the plane, and we proved the divergence form of Green's theorem. And so that's what this is for. If you're calculating the flux of a vector field in the plane, well, the divergence form of Green's theorem is a nice way to do it. Of course, alternatively, you could actually work out this particular integral around the curve, right, which we had formulas for. We flip the components and put a minus on one, and I forget off the top of my head. I have to look that up. You guys have a formula sheet though, right? So you just have to look at it. I mean, you're going to create a formula sheet, right? This isn't physics. I don't create it for you.
Is it just the front?
Yeah, just the front. Yeah, just 2 sides.
No, yeah. Okay.
Yeah. You may write on 2 sides of the paper. Regular size paper. None of this you know what I mean. All right. I'll bring in an art tablet in or something. There's a fun story in Kaku's hyperspace book about theoretical physicists doing calculations in the 80s. They got so or late 70s, they got so lengthy that they couldn't fit them on ordinary paper, so they got in the habit of carrying these 18-inch by 18-inch art tablets around so that they could write out their calculations for just that long. So none of that. Yeah. You can bring a magnifying glass if you want. That was the question.
Is it just 3x5 card, right?
No. You have a page of notes, front and back, for this one. Yeah. You're right. I did previously say a 3x5 card, but I've updated that. Yeah. Again, this should shout at you polar coordinates, right? You come to x squared plus y squared, and it's a circle which bounds a disk. If you're integrating over a disk, obviously you should use polar coordinates, right? I mean, so don't forget your RD theta, right? This one here, not much to say. We calculate the normal, and it gives us 2u, 0, 1. That gives us this as the vector area element, and then I have to evaluate the vector field at the parameterization, which gives me this exciting stuff, and then I take the dot product of this with the ds, and I get this, when I get that, and I integrate. And, all right, so. This is just plain old, straight down the middle divergence theorem question, right? So I usually ask one of these. Sometimes it's a cube, sometimes it's a sphere. This is a nice problem if I change it to a sphere, right? Wouldn't change much, right? If I had a sphere, I would be up against integrating 5y squared times the spherical volume element. So if that happened, you'd have to integrate y squared. Well, say y squared would be what? Like a what integration would happen to you if I did that? If instead of a cube we have a sphere, how does this problem change? Five y squared, but a sphere, right? So rho squared sine phi d rho d phi d theta. But what's this y squared? So we have rho to the fourth, and y is what? So we get what sine squared theta, right? So we get sine squared theta, but then a sine cubed phi d rho d phi d theta. Do you know how to integrate sine squared and sine cubed? Most of you do know how, right? Some of you are shaky on that. If you're a shaky person on that, you have a page of notes, right? So take a minute to, have some helps for yourself on how to integrate sine squared or sine cubed if you're not clear on that, right? This one here, we had outward oriented closed surface bounded by, so like x squared plus y squared equal to 1 is a cylinder, and it gets cut at 1. It just so happens that the paraboloid z equals x squared plus y squared meets at that same join, right? If we had the z equals 1 replaced with like z equals to 2, the picture would be like it is, except it would have like an upper kind of part, right? Like it doesn't have to look like that. It could look like that if the, if I had z equals to 2 instead of z equals to 1 here, it could look like that, for instance. I don't think it would have changed the problem much, though, right? We just would have then, instead of integrating from 0 to 1, well, I'd have to think about it, actually. How would we set up this region if this is z equals to 2? This down here is z equals to x squared plus y squared. So I guess we could still do, x squared plus y squared less than or equal to z less than or equal to 2. So we'd still have r squared less than or equal to z less than or equal to 2 in this like alternate problem. So I think it would just change this 1 to a 2. Everything else would stay the same if we had that instead, Any questions? I mean, again, this is divergence theorem, right? Gauss's theorem problem. But this one's got a little bit more substance to it, right? We actually had to do an integration. So these kinds of integrations do matter. It's helpful to know, yep.
So for that sheet, was the circle the boundary of the whole shape itself? Like, because I remember we talked about in the past about how, like, no matter what the shape is, you could take the integral, the flux over the boundary, and it be, or maybe I'm just totally ignoring that. That's not actually it. Like how, like if the circle, if it's not a closed object and it has a
Well, if it's not a closed object, that's a different kind of problem. But if it's a closed surface, then like divergence theorem is a good tool.
Was it?
This one's closed, yeah.
This one is closed. Oh, okay.
Yeah, I think it's said. So, outward-oriented closed surface,
Oh,
yeah.
I see it now.
So I'm just saying that there are 1,000 different ways of modifying this to a similar problem that, But close, yeah. Here's like one of the. Sometimes you get to this part of the course and you're like, wait a minute. I got this Stokes theorem. I've got this divergence theorem. Which one should I use? Well, it depends on the context, right? If somebody asks you to calculate the flux of a curl, odds are pretty high Stokes theorem is the thing to look at, right? But on the other hand, if your surface is not closed, divergence theorem can be used, but in a kind of indirect way. We have to play games like are played in this problem, I think. well, no, this one's just straight Stokes theorem. This is a verify Stokes theorem question. So like, on the one hand, I calculate the circulation of the vector field around the boundary of the upper hemisphere H, which I've illustrated in green, and then so that works out to 2 pi. So to do that, I have to, of course, parameterize. First of all, I have to come to terms with the fact that I got to go counterclockwise. If I imagine myself a little dude walking along the edge here, then the left, the surface is on my left if I'm walking this way, right? So that's counterclockwise oriented, and so these are the formulas to parameterize a counterclockwise unit circle like that, and then the line integral as works out to 2 pi. On the other hand, the flux integral, we got to calculate the curl, which is not too bad here. It's just 0, 0, 2. And then when we calculate the flux, of course, we need to know the surface area element for the sphere, but that's something you should have on your sheet. You can just quote that from class, right? We had a list of like 5 standard examples. You can use those, right? We had the sphere, the cone, graph, plane? I don't remember, but we had 5 standard examples. Some of those were kind of like uber examples, like the graph example is an example of examples, you know? Anyway, so that's the ds. This, of course, is rho hat. Also something you probably should have on your sheet. Like rho hat, phi hat, theta hat, right? You might need them. Anyway, so yeah, that just picks up the z component, which gives me this, which then I can integrate and back to 2 pi again. Well, that's good, right? If it wasn't 2 pi, something would be wrong, yeah. This one here, I'm sorry, I messed the problem up. I was supposed to have, so my apologies. I assumed you made a mistake when you asked me, but apparently not, so, sorry. Yeah. With the bottom being square rather than square rooted, this becomes, it's not conservative, right? But it does satisfy the closed condition, right? This is an example in the plane of a vector field which is satisfying the closed condition, but not conservative. Whenever I say conservative, it's with respect to a domain, right? Any domain which includes the origin for this thing, it's not conservative. Well, first of all, the origin's can't even be a point in the domain, right? Because the vector field's not defined there. There's division by 0. But if you have a domain which encloses the origin as an interior point, that won't work, because you have a loop. It'll get hung up around that origin. It's not simply connected. Because essentially the point of this is that if you calculate the circulation of this vector field around a little circle around the origin, you'll get 2 pi, no matter how small the circle is. So if you include the origin, you have an integral around a loop, which is non-zero, which means it cannot be conservative, because we proved one of the characterizations of a conservative vector field on a set is that the integral around any loop is 0, but the integral around that loop is not 0. So what the idea of this problem is to use what's called the deformation theorem. And I realize every group will get full credit for this one because I messed it up, right? So this one's free. But this was the point of the problem that I butchered. Sorry about that. But the idea, of course, is then, since it satisfies the closed condition, the integral around the boundary of the region is 0, but the integral around the boundary, it's got a counterclockwise outside edge and a clockwise inside edge, right? So if I make them both counterclockwise, I get that the integral around or if I make them either both clockwise or both counterclockwise, the integrals have to match, is the point. That's the deformation theorem. So here is the one I was sort of mumbling about 5 minutes ago. This is an example of where we can use the divergence theorem in an indirect way. See, because I'm interested in the flux through the upper hemisphere, which is not a closed surface, but if you add to the upper hemisphere the disk, that gets you a closed surface. The trouble with the given disk is that it's wrongly oriented. It's oriented upward, which means that the normal to the disk points into the upper hemispherical ball, right? Which is opposite what you want. So you need to like take account for that. So the integral over the boundary of the upper half ball is like the hemisphere minus the disk part, because again the disk has the wrong orientation. But that's equal to the integral over the divergence, which is given to be this, which works out to 20. And so at this point in my life, I was making everything work out to 42. So of course I've moved past that now, usually. Although 42 is 6 times 7, so maybe I was just anticipating things. Sorry, I'll stop. Again, problem 14 is I made a mistake here. I thought the problem made sense, but I mean, it's not wrong, it's just not right. Because the truth of the matter is, for the unit sphere, every choice of n gives you 4 pi. Yeah, every choice of n gives you 4 pi. However, if we make the radius of the sphere r, it doesn't work out to that. It's 4 pi times r to the n plus 2. So only for n equals to minus 2 is the flux independent of n. It's independent of the radius, actually. N equal to 4 pi for the unit sphere. So if you look at the, I reposted the math battle, and I've like reworded this question so that if I use this again in the future, it won't hurt. It'll be more meaningful. And I think the way I reworded it was, like, you're given that the flux of f through a sphere of any radius is 4 pi. Show n equals minus 2. That's the way I should write this. Yeah. There's other ways, but problem 15. I usually try to ask something about like proving properties of either gradient, curl, divergence, or all of the above, you know. So I gave you guys nice definitions in terms of like summations for all of these. And if you go back and I did some proofs of like properties, I do sometimes circle back to those and test on those. Those aren't hard, but they do require a little bit of preparation. It took me about an hour of class to work through all that, you know. If I spend that much class time on something, it's probably because I think it's worth testing. The exception to that is differential forms, because I'm just being ridiculous there. All right? So, anyway, so this is just definition of divergence. Here's the ordinary product rule, right, for the partial derivative. And then I just regroup. I've got, you know, this is the jth component of the gradient. And so you've got vector, the jth component of a vector times the jth component of another vector summed from j equals 1 to n. Well, that's the dot product. And again, this is just straight up the definition of divergence in n dimensions. So, this one is a new problem. I made this up just for you guys. So, the idea here was to piggyback on the previous problem. So we just figured out that the product rule for f times g is that. And so I gave you that the gradient of f is perpendicular to g, which gives you that the dot product of those two things are 0. And then I conspired to make this f and that f cancel, so that it would leave you an integral that you could do. And so yeah, that's how that happened. If I had more time and things, you know that the answer here would have been 67, but I ran out of time. The open cone, flux of the curl through the open cone, this should probably, you should be like, wait a minute. Flux of the curl, this is a Stokes theorem problem, right? Because, like, okay, why? Well, number one, you don't want to calculate the curl if you can avoid it, because it's a pain, right? It's much nicer to just integrate around the edge, and that's what we do. So the edge of the open cone is just the top rim, and so if you think about that, let's see here. If you're a little dude walking along here and you want this, you got to walk this way for it to be on your left, which means that the pictured curve with the arrows is minus the positively oriented boundary of S. So that minus appears here because Stokes' theorem requires a positively oriented boundary. But you're like, well, why don't you just, clockwise orient the curve? I mean, I guess you could. I just as a default, work with counterclockwise oriented curves, so I just put minuses in to get back to that because that's my default. Now, if you want to learn how to parameterize clockwise oriented curves, feel free, go to it. You could do that. Like you could, but anyway, so 32. And then this one is ambiguous because I didn't actually say what the orientation of the cone was, right? If I had put downward oriented cone, then that answer would be like certain. But if I had put upward oriented cone, then the answer should have been minus 32 pi. Does it make sense why the flux also has to be like another thing you might ask is like, what's the flux of the curl through the upper cap? Like just the cap at z equals to 4. It has to be what? It has to be negative 32 pi, right? Because the upper cap union with the downward oriented cone, that is the positively oriented boundary of the solid cone from z equals 0 to z equals to 4, right? And how do we know that the net flux of the curl through a closed surface is 0? Well, we had two different arguments for that, right? We could use the divergence theorem on that. So the divergence of the curl is 0. So we do know that if we're integrating over the boundary of some region, let's say E, of the curl of a vector field, right? Then I think the nicest argument is just to use the divergence theorem over, right? Because then we have, this is just 0, so this is 0. Assuming, of course, this assumes that what? It assumes it's a closed surface, which I've tried to indicate with saying it's the boundary of this volume, right? A closed surface is the boundary of a volume. So it better be a simple solid, right? The point being that the vector field has to behave, right? This doesn't have to be true if the vector field has like a divergence at some point on the surface of the solid. This does presuppose a certain niceness to the vector field for this result to be true, right? Anyway, this one here, I should have made it like the upper half shell to make it more interesting because some of you, I heard you guys talking. It's just the origin, right? Symmetry. Yeah, right, you got me. At least the mass was interesting, right? We have to integrate z squared times ds. Ds here, of course, is r squared sine phi d theta. And some integration later, I get 4/3 pi alpha r to the 4th. And, to set up the integrals for the center of mass, I have to divide by the mass and integrate the density times, x times dm, y times dm, z times dm. Little dm is delta ds here, where delta is alpha z squared. So I've got like alpha z squared times ds is the little dm, that times x integrated divided by big M gives us the average x, right? And it just so happens that these integrals, you've got a 0 to 2 pi for your cosine theta. That's 0, right? You got integral to 0 to 2 pi of the sine theta. That's 0. And this one, you got this time the theta doesn't kill it, but the phi integral kills it because when we think through 0 to pi, if we make like u equal to cosine, I think, then I'm trying to remember. Something kills it. I'm still not seeing it at the moment. Well, I think I could do that integral, and I can make u equal to sine, couldn't I? I do cosine cubed is like cosine theta times 1 minus sine squared theta. Then I'd have u equals to sine as my substitution. And then sine of 0 is 0, but sine of pi is also 0, so like the integration region. Anyway, this integral works out to 0, which is obvious from the symmetry of the problem because z squared is symmetric in the upper and lower half of the hemispherical bowl, of the bowl, the spherical shell. All right, anyway. We've done a few of these problems, right? I really don't have too much more to say here. We worked out generally that if I did it differently, it must differ by a gradient. right? This is something we worked out one day. Remember that? So that's what I'm saying. Is like this will do, but if you want any other answer, it has to be related to my answer by just adding a gradient of some other function. So when I'm checking your work, I'll see if you match what I did according to some gradient. I mean, I should be able to tell whether I should be able to find your answer in the possible adjustment of my answer. Yeah. Problem 20 is a silly problem. This is just a very convoluted way for me to ask you, is this a reasonable curl? And the answer is no, it is not, because the divergence of that is non-zero. But the divergence of the curl has to be 0. You're like, wait a minute, so if I go back and look at all the homework that you ever assigned me, and if I look at vector fields that you told me were curls, is it going to be the case that the divergence of those were all 0? And I'd like for the answer to that to be yes, but the answer is no. But you guys didn't notice, so haha. I'll tell you which one I'm talking about specifically here in a second. Part A for the last problem was fine. Part B, I messed something up. I talked myself into this being 0 when I worked out my solution. But the thing is, this isn't 0, and it ruins my calculation. And in fact, you can prove that no such vector potential exists for part B here. It's actually impossible. I see some celebration. That's good. And we could have seen that coming if we calculate the divergence of the magnetic field here. It's non-zero. It's actually 1 over rho squared. It's like, I forget what it was exactly, but it's the divergence is actually non-zero. You can see that from the spherical formula for the divergence. So this is not true. It's actually impossible. This is a lie. So at the moment, we only have, in terms of positive examples, we just have the magnetic monopole example I worked in class, right? Anyway, let's see here. Let me go back. Yeah, like specifically this one, guys. I think the odds are very, very high that this problem is nonsense. Is the divergence of this vector field 0? I don't think so. It would be quite a spectacle for it to be 0. I mean, the x component is 2x times the sinh of z. That's not usually 0. Right? So like, no, you shouldn't buy what I'm selling here. But I was trying to make something that made the use of the Stokes theorem interesting. It's just I forgot that there are certain constraints I have. Namely, I have to write down a vector field whose divergence is 0 if it's going to be the curl of another one. And this is why if you take a good look in a lot of calculus books, you'll find there aren't many problems on Stokes theorem, because they're hard to make in such a way that they're interesting. And they don't just everything devolve into 0. But anyway, do you guys have any other questions before I just meander through solutions here? Yeah.
So are there any differential forms on the test?
Yeah, I mean, I'll ask a bonus question about it, but not too. Probably won't be. I don't foresee the differential forms question on the in-class part of the test being anywhere near what I gave you guys to play with last night. Yeah. It should have worked out to 67, of course. So you're not surprised to that. I mean, you got 67? Or you said minus 67? Has anyone figured out the significance of 331? 3 plus 3 and... Yeah, 3 plus 3 is 6, and 3 plus 3 plus 1 is 7. That was not it, though. That's just a quirk. Let's see here. So, surprise attack mission 9. You're like, wait a minute, wasn't that test 3? Should I really study that at all? Yeah, I think you should. Because one of the things that you could get hung up on test 4 is integration, right? So if you have any sort of holes in your armor, let's say with respect to integration, it's a good practice to just go back and refresh your memory on how we did integrals, Not this one so much, but this one or this monstrosity here. I mean, these are not the greatest examples, but my point is, what if I had a problem where you actually had to do an integration over that, like tetrahedron bounded by the coordinate planes? Could you do it? You put z equal to whatever it is, and you have to bound x and y appropriately to set up the xy integration. Could you do that? It's usually on my final, right? So, just a thought. Let's see here. One idea that I should mention is that we just haven't run into it in the material that I've looked at. I mean, of course, these are nice problems, right? Like, you have to set up the integration over a triangular region, right? That one's interesting. Let's see here. There's something there was a mistake. The grader said there was a mistake in my solution to, man, I'm trying to remember what it was. I think it was like one of the last 2 problems I gave you guys. There was something askew there. Anyway, any questions? Oh, the thing I was thinking is, like, the thing I haven't had any problems here on, but is something I do try to test on sometimes, is the, how do you construct the potential by integration? Do you guys remember this? Like, what's the formula, given f path independent, not big F. How did we construct if this is u, right? You pick some point in there, say x naught, right? And basically you say, okay, well, I can, for any other point r in u, I can say, well, I can say f of r is the integral from x naught, right? Oh, excuse me, it's the integral along the curve of f dot dr, right? Which you could write reasonably as the integral from the point x naught to r of f dot dr. So that is something I spent considerable effort proving to you, that if we take that formula, we differentiate it, it gives us the gradient of the f is equal to the vector field which is given, right? So I would like you to be aware of that. I don't usually test directly on the proof of that because it's just a little bit tricky. All right, but anyway. Any questions? No? Yes? All right, well, I guess, oh yeah.
What's the centroid formula?
The centroid formula. Like the centroid formula, generically speaking, is x bar is equal to 1 over the mass times the integral of x dm. Y bar is equal to 1 over the mass times the integral of y dm. And z bar is equal to 1 over m, the integral of z dm, where dm is either equal to lambda ds, or sigma dA, or delta ds, or rho I don't know, I don't have a good notation for it. You know, the point is, it's always the same thing. It just depends on if we're talking about a one-dimensional object, a two-dimensional object, you know, a flat surface, a curved surface, a volume. But it's always, we take the density times the, you know, line area or a volume element. That gives me the little dm, and then I multiply that by x, do that integral over the appropriate line, surface, or volume, and then I have to divide by m. Of course, m is the integral of dm over the object, right? But so I like to think of it this way, because that way I don't have 30 formulas to remember. I just have these 3, and it's just the same thing in different contexts. But are there other questions? I feel like that was, people were announcing they were done with their VAC hacks, so I'm going to take it under advisement.